Also,
started.
okay, so also it's kind of like hard to keep track of the chat, so you were recommended to speak. Yeah. So first we have this problem. Um, this is like a buffer problem, kind of like, yeah, let's just start off lightly. So yeah, try this problem. If you don't understand the statement, then you can ask. Everyone understands the statement, right?
Yeah.
Oh wow, I wonder who this is. Okay, I will just explain it nevertheless. So yeah, so divs of n is like the set of positive divisors of n, like for say um, there's a divisor set. A positive integer m is called f cool if there exists a positive integer n for such that like the polynomial that say we have 6. And we have some other numbers, say 16. Not 16. Say you have 8. Then this polynomial maps this to this. Like it could happen that f of 1 is 2 and f of 2 is 4, f of 3 is 8, and f of 6 is 1. Something like this. And you have to prove that there are finitely many f cool integers. So a natural way to start is to like begin with like contradiction that say you have infinitely many cool integers. So any ideas? Hello. Okay, if you need like more time to try the problem, then sure. I'll wait for like 2-3 minutes more. Yeah, the notation is kind of hard. I understand. It's kind of hard to work with at first, but like yeah, it gets better. Yes, as Mr. or Mrs. Meow says. Okay, let's just consider like two numbers which are like cool. Oh, nice. You're getting hang of it. But anyways, let's just consider like two numbers which are cool conjugates. Let's like call these two numbers, if they satisfy this relation, cool conjugates. Because why not? And suppose they have the divisors. Also note that they have to have like equal divisors, like equal number. Then say like di are the divisors of m and ei are the divisors of n. Can you think of anything from this? Okay, when I first when I was first trying this problem, the first thing that came to my mind when like I saw this was an old ISLNT, which I don't remember. I think it's like 2002 IMO1 or something. Not sure. It's not really related, but yeah. So, any ideas? Think about what happens when the numbers grow large. Like, since you have assumed for the sake of contradiction that that there are infinitely many such like cool integers, which means there are infinitely many cool conjugates. What happened? So yes, f of e1 equals e1 is first. Can you say why? Like, can you speak up, please? If you can't, then you can even type in chat. It's fine.
Yeah, this is because eventually the function keeps like function becomes increasing, and so you can see this.
Yeah, exactly. Polynomials grow like fast, so they become increasing, and they have to like. And in fact, it's not only that f of d1 is e1. You can say that like this. Because like eventually the distances between these grow large enough and they're always increasing that they have to like be equal to each other. Does this make sense to everyone?
Yes.
Also like to avoid like some hassle which we might get into, like say we don't want like negative numbers to be here, right? So let's just assume that leading coefficient is like positive. Um, Say degree of the polynomial is d, and leading coefficient is positive. This is a notation I just use for leading coefficient. Looks cool.
पहलवानी को बोला है standard.
Oh, is it standard? Wow.
I don't know. और
Okay, nice. Also, this necessarily doesn't happen for like very small numbers because polynomials can behave weirdly.
बैलेंस बना के चले like line it feels like you can Lagrange like the polynomial should be determined.
I'm sorry, but I couldn't hear you. If you can't speak, then you can obviously write in chat. Can you somehow Lagrange? Okay, like for huge numbers. Okay, how exactly? This is something I actually tried when I was like first doing the problem. So it's interesting that people are thinking about the same way. Like for huge numbers. What exactly? What exactly do you mean by huge numbers? Like how? Also, just like as a hint, this is an int poly class. So we will probably need some divisibility stuff or something. Like this is an integer polynomial, of course. So you have to use some divisibility stuff. So think about that. And for the Lagrange interpolation,
Can you show me the problem?
okay, the problem is this. You can probably take like a screenshot because we are working like much below.
Okay, fine. I've taken a screenshot. Move on.
Yeah, like talking about the Lagrange interpolation stuff, like yeah, it makes sense to like interpolate with this numbers, right? This numbers. But do they necessarily help you? Yeah, this kind of way. Exactly. And I'm unaware of a solution that uses Lagrange.
Why is f of di equals di for all I?
The thing is like,
Yeah, how do you
like
compute the like higher indices? Like, what if like if the devices grow small? How do you compute in that case?
Wait, sorry. What?
If your divisors like, how do you compute something like f of dA for like the last three divisors? You have this thing to hold as well. They can be small, right? So the size argument does not work.
I mean, as the polynomial grows larger, the distance between the divisors will increase, right?
No, no. What if the divisors are small? Is what I'm saying. Like, so for example, dA and
Uh-huh.
dA can be small. dA minus one and EA minus one can be small.
Okay,
So
I
you can
see.
choose what all the indices.
Um, hmm, it shouldn't be a problem. Okay, let me actually think. I mean, still, you will have the thing to be like increasing, like, which should suffice.
But wait, how can you comment something like f of 2 is equal to 2?
Yeah, exactly something like that. That's. I think it still holds for sure for the higher devices, but for the lower devices, I don't think we can make a stronger statement.
Yeah, like this will hold for all, like there should be a lower bound than TI which hold like, yeah.
But you can write, like, if it holds for higher divisors, you can, like, write it for like this, right? This should hold because, wait. Okay, wow, this is an issue we have to fix. Okay, so for, okay, say for like, um, for large enough stuff, we have this, of course. Now you can say this.
How is the last thing coming?
What?
Like f of m over e7.
Oh, because they are also divisors, right? Like this is basically the biggest. This is
Yes,
basically
yes, yes.
E1.
Sorry, sorry.
Okay, so so f of one is not one, right? And f of one is like f of one also maps to something here. Okay, not here, but like, and that's it. and it divides n as well. So this should be bounded. What is it? Yeah, this should be bounded, right? Which should also force like smaller divisors to be. Do people get what I just said?
Yeah.
Okay, never mind. Let's just like not use this.
Yeah, but I think the fact that smallest divisor of n is bounded, that is true, right? Like you don't need f of dizi for all of
This is too strong.
Yeah, that's I don't think. But smallest divisor of n is bounded. This is true.
Okay, this means I have to edit my AOP solution. But yeah, I think I have found a fix, which is nice. So then, does anyone like have ideas to like go from here? Luckily, the proof idea remains the same. So yeah.
I think you don't need more than like you don't actually. I don't think you need a dA f of dA equals f of ea even for the lower terms. I think only the first one suffices. So like after you find something like ea is bounded, then you can. I think that implies that dA is bounded because of the equation,
Yes.
and then I think you can say that I think dA is bounded. So yeah, so you have like dA divides m, right? So there are only like finitely many dA, but if there are infinitely many m, then some guy divides like infinitely many of them, and so you get an equation satisfying something like f of m by dA divides f of m, right?
Yeah.
So this basically holds for infinitely many m with the fixed dA. So so this so this basically means like f of m by dA equals to something times fm.
Yeah, and then you can force like this to be like a multiplicative thing, and then you can like do stuff.
Right, right.
Yeah, and this will equal like some polynomials. And since you have this, f of m will be like this. And can anyone tell me the finish from here? Okay, in fact, the constant will be like, I think, yeah, the constant will be like 1. So
What
why
the
is this?
constant is?
Like it
Constant
will
is
be 1.
like then f of 1 is one contradiction.
Yeah, right. So we had in the problem that f of 1 is not equal to 1. But if you like plug in here, you get this, which is bad. Okay, so it was one hell of a ride. So summarize the proof because I believe it would be hard for some people to follow. So first of all, we assume that infinitely many such cool integers exist. And then we listed out these divisors. Then I made a wrong claim. Like this is true. This holds for like large enough stuff. But this is not necessarily true. Like especially like for smaller cases, it's hard to control. But luckily we don't need this. Um, yeah, and dA is bounded because you have f of 1 to be f of 1 in the set as well, which implies that EA is also bounded. And then you have infinitely many m because like it's bounded, such that this relation holds. And from here you can imply that it's like f of 1 is the form of f of m by dA and some polynomial q multiplied by it, because like this relation holds for infinitely many stuff, and you can like solve this to get x to the power d, and there's a contradiction. So is that clear to everyone?
Yeah.
And what about others? If you can't speak, then you can let me know in the chat as well. Okay, so yeah, this part is instructive problem, but I think this is even more instructive. So you have a monic integer polynomial. Prove that there exists like lots of integers, like two integers, such that like in this interval, such that P of A is like congruent to P of B modulo 101. And actually 10 and 101 kind of matter, which is cool. So any ideas? Like the first thing that comes to
One thing is like P of A minus P of B, then A minus P divides them.
sorry, but can you repeat?
I mean, like P of A congruent to P of B, like you can, I think you can use A minus B divides this.
Okay. Yes.
And now you want to show 101 divides it for some. So maybe choosing A and B properly.
But that's
Wait,
not
it won't
possible.
work. Yes, it is not possible.
It's
Okay,
not
fine.
possible.
Arrange. Okay.
Okay, the thing you like after trying the problem for some time, you realize that it's like very hard to directly attack the problem.
You get like modulo 101, each residue is attained by P.
Each residue is?
Like there exists a case that P of K is any residue modulo 101.
Okay.
Like it forms the complete residue system.
So basically, it's saying that it's not bijective, modulo 101.
Yes.
So what we do is like, like every other problem. So suppose it's bijective.
Okay, mainly Vishnu, so it's not injective, right?
Um, it is injective, like mod 101. If it's not, then we are done. So where do we go from here?
I don't know, maybe take sums or something.
Okay, since like it's very hard to control it locally, we need to think of something global. That's the
Sums and something.
somewhat. Sorry, I couldn't hear.
Okay, I'm speaking randomly, but like, is it possible like we take some sort of sum like which
Yeah,
adds all
yeah,
of
that's
them?
the idea. In fact, that's
Yes. I am 2005, whatever it was, people, whatever. It was
2000.
6 people, whatever it was. Fixed points.
Oh, we have another IMO problem with a similar idea today.
Amazing.
What a star cast of problems we have. Okay, so what happens when you like sum these modulo 101?
It's divisible by 101, I think.
Like yeah, like all of them are distinct residues, right?
Yeah.
And there is this, and there's zero more. 101. Okay, what if like we squared
Okay, sorry. Why you did not write 100?
zero? Okay.
Wait, not
Oops,
101.
oops. Yeah, but still it's like yeah, divisible by 100.
Is it? No.
It is, of course.
I mean, divisible by 101, right?
Yeah.
Without 100, it won't have you.
Uh,
I mean, okay, let's just leave it. Sorry.
okay, so what happens when you like square these? There is a formula for this.
Yes.
Something. And since 101 is a prime and this is an integer, we won't do the calculations and simply write zero.
Fine.
Okay, wow. So this is like zero a lot of the times, right? But is it always zero?
I
Have you
think you
seen
can
some?
end up. I mean,
Um,
wait, yes.
have you seen this before? Like
No,
this?
no. Wait, what? Yeah.
Notice that 101 is a prime.
Yes.
So this sum is like this. Now have you
Yes. This one is well known.
Okay, so what like does this sum evaluate to?
Okay, this I have to look at. So it's like if p minus 1 divides x, then it goes to p minus 1 only. I think.
So it's 0 if it's like anything else, and if it
Yeah,
what happens if p minus 1 divides x?
I don't know. You take primitive roots. I don't remember. I remember the
Yeah,
proof, but I
like
don't
I'm
remember the
not
result.
talking about the proof. Like what is the
I
result?
don't remember the result.
Okay, actually, was it 1 or minus 1? Or minus 1?
-1.
Yeah, expected so. So do people know this proof, like the proof of this identity? Or shall we prove it? Like if most of the people know, then we can just skip it and we will end up doing more problems. So I'm assuming like, wait, what? The host does not allow people to. Oh, nice. Okay, so I'm assuming that most people know the proof of this is like by primitive roots. You take a primitive root and like some stuff. Like it's a GP and then yeah, something happens. Like basically inverse exists like in one case, and in the other case the inverse doesn't exist. So you get 0 everywhere once, and like in the other case you get -1. So here we have like, so what if you like take x equals 100? It's -1, right? Now suppose like p of x is, what if we like evaluate the same thing in a different way? Like we're basically double counting. This is not very hard from here. Like if you have the idea, like the idea is very hard to come up with. So yeah, try it. Anyone? Okay, so if you do this, this is like very scary. So what do you think this is like? Module of 101, this quantity. Like if you expand it, then you will have like a lot of terms and a lot of terms and so on. Or maybe you can do something clever. Okay, actually it turns out that hello. It actually turns out that summing the powers of 100 don't work. Anyway, and like of course you get some residue, but it like doesn't necessarily give you a contradiction. It's like the same. You get -1 here as well. So what else can we do? Like obviously summing the powers of 100 is intuitive because you have this.
We haven't used the fact that P is a monic polynomial with degree 10, so probably I think using that.
Sorry, can you repeat? Your voice is kind of like unclear.
I said that we have not used the fact that P is a monic polynomial with degree 10, so I think we should do something involving that.
Right. It is a monic polynomial. So this is one. So the thing is, if you sum this, like you will have some modular like big x to the power 1000 or something term, and you'll have rest of stuff, and you can compute it to be -1. So in a lot of cases, like in multiples of 10, you get like -1, right?
By the way, are you writing something on screen?
What?
Are you writing something on screen?
Oh, sorry. The, okay, I'm so sorry. The screen share was paused. Okay, so basically, if you expand this, you get this, right? And C of n is actually 1. So you get this is modulo some big 1000 power sum plus other things. all the other things become 0 because you have powers of like 99, 98, which are always 0. And this becomes -1. Wait, this becomes 0 also, right? Because it doesn't divide 101. Okay, no, it becomes -1 because 100 divides this. So there is not a contradiction because we had in the first count we also had -1, and in the second count we also had -1. Our goal is to like double count in a way that we get different residues, which would be a contradiction. Does everyone follow this? So here you got this because like this is divisible by 100. Another number which is smaller and is divisible by 100 is 100 itself. And to get that in this sum, you just need a power of 10. So instead, if you sum powers of 10, you would get 0 mod 101 because all of them are distinct in powers of 10, so 0. And if you like evaluated this again with powers of 10, you would still have a x to the power 100 term at the beginning because it's a monic polynomial, and other stuff which are all 0 because they are sum of powers of 99, 98, and so on. And this is -1, while this is 0, which is a contradiction. Does everyone follow this proof?
Yes.
If you want me to like summarize the proof and highlight the ideas again, then I can for sure do that. There's a really tricky problem that's like thinking of global in general is like hard when it comes to in poly because you are always thinking of like divisibility stuff or like Hensel lemma or like
Um,
lifting
yes.
roots
Hmm.
and everything. So
By the way, like, is there like, say, like, taking sums of all residues directly, like simply p of 0 plus p of 1 and blah blah blah. Like this part is intuitive, and but like the way you took the powers higher, like a square level, like we tried 100, then 10 suddenly worked. Like it is common, like when you are considering global sums, you take like you consider the sum of squares of like nth powers.
yeah, kind of. I think there is this very famous problem which goes prove that 10 to the power 10 to the power 10 to the power n plus 10 to the power 10 to the power n plus 10 to the power n minus 1. Have you people done this? I think Atul,
Not right, not right.
okay, then I will not spoil it. But then I think Atul did it in some problem solving session. And yeah, if you solve this, like prove that. You will realize how similar this two problems are, although like they are completely unrelated. Like at least I feel so. Okay, now we have some choice since we have not too much time left. We either do another problem with a global idea. I think you might have seen this, so we can skip it. Should we do like a poll? I'm not sure how.
Oh, I think you can just ask out here.
Um. Okay. Okay. Anyways, people just tell me in chat like, what do you want to do? Do you want to do this globalish problem, or do you want to learn something new like Hensel's lemma and how to use it? Its proof. How the tables have done. Okay. So let's do Hensel's lemma. Family. So this is what the lemma states. You have an integer polynomial and a prime piece is that it doesn't divide the derivative of that polynomial at that point, and p of n is some modulo p. Then you can find a sequence such that this and this happens. So this looks very complicated, but actually it isn't. What it's saying is basically, say you have this. The original statement of Hensel's lemma is for like just 0 mod p, but it can be like easily generalized to any residue modulo p or modulo p by k. Yeah, so you have this. So this is a root of the polynomial mod p. But what happens in mod of p square? No one knows. It can be 0, it can be p, it can be like um, so all of these values are possible to be attained. So we don't really know for sure. So it would be nice that if we know a way to like construct all of these. That's where Hensel's lemma comes. So there is an identity which goes like this. We will prove it, don't worry. Have you seen this before, by the way?
No.
This is like extremely useful and a lot of problems. And it has like two proofs, like Hensel's lemma basically follows from this. And you can generalize the 2 to k and k to the power minus 1. So do you want to like look? So the first proof is like, so you have one like normal proof, like of course, and you have one which uses like kind of calculus by like Taylor series.
Wait, what is this PP?
What is what?
Like you have written P of x plus T sub P. What is T sub P?
P of where is P sub P?
What is that? Like P dash x.
Oh, P dash X is like the derivative of the
No, no,
polynomial.
derivative is fine. Like what you have written earlier. T sub P.
No, TP, T times P.
Oh, fine.
Also, you have that P dash X is like doesn't divide P. Like, we had it in the statement because if it does, then this is like 0 mod P square, and this is not necessarily always true. This is true for like certainty. Like that's the point of Hensel's lemma. You want roots. So for certainty, which like for a unique t, in fact, this thing will become 0.
Okay.
And we can generalize it in like any residue. So like we're writing it like this. Okay, so let's look at the Taylor series proof because I like it. Suppose the degree is n of the polynomial set. Now consider the Taylor series expansion at like for some like a or something. So this is the Taylor series expansion. So is everyone fine with it?
Sure.
Now, if we like plug in like x equals a plus t paid by k, this will be like, and so on. And since we're looking like only one step ahead, like if you have p to the power k, then we look like mod p to the power k plus 1. Because we are like lifting from one power to another power. And notice that like this is an integer. Can anyone tell me why?
Okay, like you differentiate twice, you would at least you would get two. Like you would get two from every term. Like
Yeah, so
differentiating twice would give you at least one even term, and then for similar reasoning follows.
yeah, like basically this becomes a binomial coefficient.
Oh, is it?
Yeah.
Okay.
Okay, I will expand it. Why not? Like for in general. Um, it's a binomial coefficient. The proof goes like
It's just computation, right?
yeah, kind of computation. So basically you prove it for like f equals x to the power k, and since polynomials are like additive,
Yes.
this follows like, and this becomes a binomial coefficient, so it's of course an integer, and since like polynomials are additive and you have integer polynomials, this will also be an integer. So when you look mod p to the power k plus 1, this is obviously bigger than k plus 1, like 2k, unless it's like 1. And even if it's 1, we don't care, like it disappears because, yeah. So we only care about this part because everything else disappears mod p to the power k plus 1.
True.
Now, does this look like this identity?
Yes.
Yeah, it's the exact same thing, like for k equals 1.
Yes. Yes.
So Hensel's lemma basically tells you that you can like produce distinct residues with this, like by varying t.
Oh,
That's what Hensel's lemma is. And now if we look at like the definition again, it makes much more sense. Like this thing is basically saying that and this looks like the thing we had here, right?
can you scroll down a little?
Um, yeah, like this. And by varying t, since this is like a linear congruence, you can get unique residues for every t.
Yes.
Yeah, so you get like any c you want. Now we do a problem which is kind of a direct application of like Hensel's lemma. Let me find where is it?
I'm sorry, like for the last one, can you just summarize like what Hensel's lemma gives? Not
Okay.
the proof, like just
Wait,
final
one
result.
second. Okay. Yeah, so Hensel's lemma basically lets you construct residues of higher powers if you know residues of lower powers. Like, say you have this. Say you know like p of x is c mod stuff, like mod p.
Okay.
And always remember the fact that we need this, else the thing breaks because
Okay.
it breaks because if p dash x is divisible by p, this is 0. Then you can't like vary t to do anything. It's like this mod.
Okay. Okay.
And we can use this to our advantage in many problems, like to get some contradiction or something. By the way, it's pi time. Okay. So now let x plus tp. So this is a1. This is a2. Now you can vary like
So it is like you know one residue in mod P, then you can get control of some, then you can get all residues via to mod P square under assumption that derivative thing is not divisible by P.
Yeah, exactly.
Okay, fine. Thank you.
Basically, you like use a2 as the x in the next equation, like x plus tp square, and like a2, which is like x plus tp, and they are all the same mod p to the power k, like the next residue, like the next prime power.
Yes.
So here is the problem. Prove that so this is the problem. The case like m equals 1 is like FLT.
Yes.
Because then you can basically choose x equals 1 till p minus 1. So you want to like move up.
Hmm.
I'm giving you all like 2-3 minutes to try. This is not hard, sorry. Okay, since like it's kind of like
We
sorry.
have to induct, right?
Yeah, so yeah, so done by end. Yeah, so you end up obviously as Kruthard says. So assume that this is true for some m. Oh, that trip cancel. It's fine.
I was confused for a second. Yeah, I thought he maybe said in chat.
Wait, what? Like it shows that Kruthard told me this and so. Anyways. Oh, yeah, sure. So first of all, our polynomials is And the derivative of the polynomial is and this is co-prime to like p. So yes, we can do Hensel stuff. So now you just like do Hensels and prove like you can vary t for like all the things because there is only like one thing in. Okay, never mind. I will just explain nicely. So like there exists t such that and now like you can vary these individually like for some value of x you'll have some value of t, so you will get p minus 1 things for the set 1 to p minus 1. Now the thing is you have to prove that these are the only solutions. Now if you suppose that like you have another solution k, then it turns out that it's already in the set because like if this is true, y is some x. Okay, let's say xi and di. And it's some xj modulo p to the power k, which means it was already in the set. So it can't be like a distinct solution. So we indeed have p minus 1 solutions. I hope this is clear to everyone. Okay, so now we move on finally to a very cool problem, which probably will be the last problem of this session because we don't have much time left. Not really. No, I can't say. If I give a nuke now, then we would have to stay here till like 6 p.m. Okay, sadly, I don't have like the problem copy paste like on my clipboard, so I will just try.
Wait, is this from PFP?
Yeah, it is from PFTV. Like this fairly well known. So I try this problem for some minutes, for a few minutes. I mean, you can still tell us some ideas.
I mean, I read the solution in the book. So
Okay, that's okay. So, um, in the first class, we proved this thing. And from this, we have that P f of n divides f of n plus f of n, which implies n divides n plus f of n. And this implies that n divides f of n. So we have some progress. But what do we do from here? But this also implies that f of 0 is 0. Because you can write f of n equals n to the power k g of n.
Yeah, I think we can now substitute this.
Yeah. So you want to work with g now,
Yeah,
which is not divisible by n, which like n doesn't divide g of n. Because we are taking like the highest power.
yeah.
So g of 0 is not 0. Okay, so let's take a prime that divides g of m. This is a natural thing to do.
Okay, GN or GM?
It it doesn't matter, does it?
I mean, like in the assertion N or M.
Um, wait, what?
Oh, okay, actually, never mind. Fine. Okay.
Yeah, it's so you want to prove that g of g is like, okay, let's try to like guess the solution. Obviously x to the power n is a solution.
I think C into X to the power N.
Yeah, c into x to the power n works as well. And these seem like the only solutions. Like we saw in the Canada problem, that if you have something like this, then the answer is like x to the power d or x to the power n. And this is like very similar. Oh, by the way, by the Canada problem, I mean the divisibility problem. It was 2023 Canada MOP4. So what we are doing is like, so this is quite intuitive that this is the only function that satisfies the thing. So we want to prove that g is like constant. And what we do with constant polynomials is like, we can use like take advantage of the fact that most primes don't divide them because they are very small. And we have that p divides g of m. So like for now we can assume this, of course, because we don't have like proof that says g is constant. But in general, like if you look in a god's eye view, then this is bad. So you want to like take bad stuff and prove that it can't happen. Like you want as extreme statements as possible to contradict something, right? And something even stronger would be taking a prime power dividing g of m. But can you like guarantee that a prime power always divides a polynomial which is like non-constant for some m? So our question for now is, and you probably can find like one p or something, but can you like say, like even if it's like constant, you can find one such p, but can you find like a lot of p's, like possibly infinitely many?
Like if G is non-constant, you can, right?
Yeah, but what's the proof?
By Hensel.
How exactly by Hensel?
Like set of primes dividing GM, like set of primes dividing G is infinite if G is not constant by exponent. You can just lift the exponent.
You can lift it to like p to the power k and find m.
Yeah.
But do you like? Okay, yeah, you can do that because by Schur's theorem, you'll have like infinitely many times dividing polynomials, like
Yeah.
non-constant.
Yeah.
Another proof of this, which is like quite clever and interesting, is that you first um with the this is like product of irreducible polynomials like G, like in integers that is. So what you do is take the derivative of one of them. And see, since these polynomials are like irreducible, they're also coprime. And now, what do we do when we have like coprime polynomials? Yes, we use Bazooch. So for some polynomials A and B, you have that. Now, if you take like a very big prime dividing F, and like very big as in like greater than C, then T doesn't divide F1 dash. Also, yeah, like that's what I wanted to say. Like you can obviously Hensel's, but you have to prove that the derivative is like coprime, right?
Oh, fine.
So for that exact reason, you need this. Like the proof is fine. Like uh, you can like probably get away with it, but yeah. And this implies that this is like not divisible by p. So now you can Hensel once again, like Muller said, and you can find prime powers that by polynomials. So we came off a tangent. We can off the tangent. We need this in this problem. Okay, so now we do something really clever. We consider like a very big prime. Very big as in like greater than G naught. Because yeah, there's like the constant term of the polynomial, like, and we know that it's not zero. So it's fine. We and unlike P doesn't divide G of P for obvious reasons. Like we had that N doesn't divide G of N.
Yeah.
So by CRT we can find an N. Like we picked like M is by the way like specific. Like yeah, so we chose m such that like p divided by k divides it. So we choose n such that like m mod kilo mod p divided by k, and also this. And we all obviously have a solution because these two are co-prime. And now this implies, as you can see, this is basically Hensel's, right? Like this like lifting from m to n. And from here you can imply that since you know that p divided k divides g of m, so you're basically lifting from m to n. So you have that p divided k also divides g of n, since like they're the same modulo p divided k, right? Because you're lifting. Okay, you're not even like lifting because and if you lifted, then you would need a choice of t, but you don't need that because they're like the same prime. And you also have with this that g of p divides g of n. And you can combine this together to get this. Because we know that p divided kg of p is just f of p. And g of n divides f of n. Which implies p divides n. Which is a contradiction.
So,
Yeah, this is like very clever. Um, yeah, like when I first saw the proof, I had no clue how to motivate. Yeah, and this is impossible as p divides g naught. Yeah, and this is bad. So g is constant and f is cx to the power n. I think the motivation behind this is that, as I said, like you need something extreme, like as extreme you can like go to force something bad. I think it's like very important to look in a God's eye view, like which will like the things that will be wrong, but you don't really have that. So you assume you have that and prove that you can't have that. That's I think is a really good thought process in general when you like when it comes to these kind of problems. And sadly, I couldn't cover like a lot of problems which I planned to. So either we can do like I will still like give you the sources away, but we might do another session of it polling. Might. So, yeah.
so can I stop screen share? Can I stop the recording?
Like after I like show
Oh,
the
okay, sure.
so I had these problems and like the Hensel street. Um, some of them are like like not complete statements, but you can like find these in PFTB. Like we did this. This in PFTB. These are Olympiad problems, and some other problems include probably this. Don't worry, this doesn't spoil this problem at all because there are like 50 different solutions to this. And yeah, there are lots of impossible problems also. There's like Elmo 2013 and 1. So next sessions we might do these things. Looks cool. Yeah, you can stop recording.
Okay.